Hello, welcome along to HOLOPLOT HQ in Berlin and to the second webinar in our series introducing the HOLOPLOT X1. Today, the title of our presentation is a 10,000 square meter space served by only 9 loudspeaker positions. How to generate unmatched intelligibility thanks to X1 coverage beams. Now, I know what you're thinking, that's not a very punchy title. However, actually, what I hope you're thinking is, wow, a 10,000 square meter space served by only 9 loudspeaker positions. It's an amazing thing. We've got a case study coming up where we talk all about that, and we'll go into that in a second. Now, to present this case study, I have my esteemed colleague, Emad El-Saghir, a fellow here at HOLOPLOT, and an industry name I'm sure many of you are very familiar with. So let's go into a quick recap of what we covered last time. So last time we did this introduction into HOLOPLOT X1, we ran through a lot of them sort of capabilities of HOLOPLOT X1 and the main technology pillars. So looking at the main technology pillars, here we go. So on one side, we have the wave field synthesis functionality, and there we looked at virtual sources, what virtual sources are, how we use them, and how they can really add to your immersive experience when you're using it as a sound designer. Then on the other side, we have 3D audio beamforming. Now, in that side of it, we looked at parametric beams. Now, these are beams that can be steered dynamically, both horizontally and vertically, adjusting the beam height and the beam width, but also the steering angle of the beam as well. And we also then looked at coverage beams, and coverage beams is what we're going to go into a little more detail today. A coverage beam, so it's a beam that is got some pre-optimization, a beam that is actually optimized for an audience area, both for homogeneity or evenness of the coverage and for spectral uniformity. But we'll go into more detail in that shortly. So just to cover what we're actually going to look at today. So first of all, we're going to look at why did loudspeaker technology need to advance? You know, why do we even need coverage beams? Why have we got to this point with technology now that we're able to cover these audience areas in the way that we are? Then why do we need coverage beams at all? How do we work with coverage beams? So looking at our workflow, which is something I'm sure you're sort of very interested in terms of how we set those up and how we work through that process. And then we look at why a coverage beam is successful. And then we look at the real world deployment. And that's when Emad will take over and go into the case study and the detail of that. So here we go, let's get into it. So first of all, why did loudspeaker technology need to advance? Well, first of all, we don't always get to work in the easiest of spaces as sound designers or electroacoustic designers. And often we get put into acoustically challenging environments. And what does that kind of entail? Well, you know, common spaces as far as acoustically challenging environments are concerned. So we've got like houses of worship, and in the image you saw previously, then we've got a mosque, very, very large mosque, and that's going to be part of the case study. We also got transportation hubs, where we've got, you know, very sort of wide range of spaces that we have to look at in there, whether it's very large atriums or even kind of subterranean platforms, where we've got very high background noise levels, and very sort of difficult conditions and almost acoustically hostile environments that we have to work in. And then convention centers, again, with these large atrium spaces, but also smaller areas and different areas that you need to cover. And sports arenas, again, high background noise levels, but very, very large, wide open spaces that we need to cover. So let's look at this. So what are sort of the challenging factors? And I've just been through a few of those. So you know, as we're talking about these high volume spaces, and you know what comes alongside high volume spaces usually is quite a high reverberation time. We also have these hard reflected surfaces where we get unwanted reflections, audible echoes come into play, and things that we need to control with these hard reflective surfaces. Then high background noise levels, and as we've seen kind of in transportation hubs and in kind of sports arenas and the likes, we can have very, very high background noise levels, you know, upwards of 80 dB, 80, 90 dB in times. So we've always been, you know, real challenges that we've got to work against there. And then architectural constraints on the loudspeaker integration. So, you know, often there's kind of, you know, we work in listed buildings and it's very difficult to kind of make alterations to the buildings. the overall architectural design or the vision is sometimes very difficult to change. And we often spend, time battling with architects over where we can place a loudspeaker, where is acceptable in the design. And we're all kind of trying to work together in order to kind of see that vision through. And often that means that either you have to compromise as a loudspeaker designer, or the actual architectural design gets compromised. And what we're always trying to do is, trying to make that compromise as little as possible. And then in order to meet these challenges, how do we require the system to perform? So let's have a quick look at that. So looking at sort of maybe design targets that we often get given as loudspeaker designers or system designers. So what we want is sort of adequately loud with kind of homogeneous distribution, so an evenness of the coverage, so all the way across the space that you're trying to cover. And when we talk about adequately loud, notice that we don't say as loud as you can possibly get it, because often in terms of speech intelligibility, we don't actually want to go as loud as we possibly can get it. And we know kind of, looking at the curves as far as speech intelligibility is concerned, when we push beyond 87 dB, then actually we start to plateau off in terms of how much we can improve the intelligibility beyond that particular level. Then let's look at kind of minimizing kind of unwanted reflections and kind of this echo probability. And we're constantly trying to do that. And we're constantly trying to control sound. And obviously here at HOLOPLOT, that's something that, we're really kind of pushing forward and pioneering in terms of our ability to control sound, both in the horizontal and the vertical planes. And we'll look at that more in detail in a second. Then minimum interference between arrays and adjacent areas. So interference, sort of the phase interference between loudspeaker positions, but also with adjacent areas. Let's say when we're looking at a train station and we have two platforms, when you have a PA system on one side and one on an adjacent space, it actually acts as a noise source and drives down the intelligibility on the other platform, as much as 0.1 in SDI at times. So we have to be really careful in terms of how we control sound and not push it into spaces that we don't want. And then, as we say, we want to achieve this high speech intelligibility. So what do we talk about when we talk about the speech intelligibility? Well, here's kind of a description here, really, in terms of what we talk about there. So speech intelligibility is a measure of the effectiveness of understanding speech, ultimately. And there's kind of a number of functions that play into that. So it's the absolute signal level, which is what we just talked about in terms of achieving this adequate level in order to achieve the optimum signal level and speech intelligibility there. The signal to noise ratio. So again, the background noise comes into play, and constantly in all the different frequency bands, achieving kind of above 10 to 15 dB above that background noise level allows you to then optimize in terms of that intelligibility and achieve that signal to noise ratio. We have the direct to reverberant ratio, and now we're talking again about the unwanted reflections, the audible echoes, and being able to control sound and getting the most direct sound and reducing the amount of reverberant sound, and reflected sound that we get. So, I mean, there's several other factors that come into play there. And you can see on the right-hand side, in terms of the table, what we're trying to achieve a lot of the time is this kind of 0.54, where we look at this good quality PA system. And often in kind of acoustically challenging environments, that gets dropped down to sort of the 0.5, and especially when we're looking at VA systems. But actually what we really want to do is push that up, and we actually want to achieve really good speech intelligibility, the highest quality that we can get, really, obviously with the restrictions of budget and everything that comes into play on a project. So then, sort of what are the design considerations, I suppose, then, when we are actually sort of designing for this optimal speech intelligibility? Well, we look at sort of a number of factors, and they're kind of listed out here, really. So speaker integration, how many speakers, where we place those speakers, what kind of speakers, we look at that. Then we look at the room acoustics, again, controlling the sound within the space, looking at the reverberation time in the space, and not exciting the room to the point that you're driving down this intelligibility again. And then the architectural design and how we manage that and how we're able to integrate within that. So let's look at that in slightly more detail. So conventional approaches in terms of sort of loudspeaker design, well, we've got this kind of centralized approach, but we've also, first of all, got this sort of distributed approach here. And the distributed approach we see quite commonly in terms of putting lots of smaller loudspeakers across a space to be able to achieve the speech intelligibility and being able to not excite the space in the way that we want. But often it's difficult to achieve this, especially if you don't want to impact onto the architectural design. If you don't have totems, columns, pillars to actually mount loudspeakers to, if you're not able to put them into canopies or ceilings with kind of a false ceiling within there to actually be able to integrate those, then it can be difficult to actually do them in a number of spaces. And then the centralized deployment that you see here on the right hand side at the bottom, and obviously you need a lot of control to be able to do that, because when you're using one centralized large array and you don't have the control both in the horizontal and the vertical, then a lot of the time you will excite the space too much, and again driving down that intelligibility through lack of control. So, I mean, just a very sort of quick overview in terms of sort of this direct to reverberant ratio, and I think this is kind of I think we're all very aware of this in terms of what I'm talking about. So looking at the direct sound from the source to the listener, the most direct path that can go to that point. Then looking beyond that, then sort of we bring a couple more types of reflection into play. We bring kind of the early reflections into play, and you can see here it's a reflection off like one wall, something that arrives very quickly after that first direct sound. And that will kind of add to that sense of reverberation. And then we've got these late reflections that come in, and they can be very late when we've got these really large open spaces and clearly come back as very clear audible echoes. And that's really something that we want to control, and something that has a great impact on intelligibility. So yeah, just to kind of sum that up then, and then going through then into architectural design. So this is kind of maintaining that sort of creative vision that I talked about before. So, a lot of the time we're looking to kind of have sort of concealed integration. So we don't want to see the technology. I'm sure we often have conversations like that as sort of sound system designers with architects and with clients. We want to be able to hear it. We want the high intelligibility, but we don't want to be able to see the technology. And that's something that we often come across. And this is something we'll look at as part of the case study, how we've kind of dealt with that challenge within that. And then fewer mounting points. So reducing the number of mounting points. And again, when we look at sort of a distributed system, really wanting to kind of reduce that down, which has a number of benefits that come with that. I'll talk about in a second. And then kind of this even coverage over large open plan spaces and being able to do that from a single point. That's a really sort of good goal to try and achieve. And you always want everyone in your audience area to have the same experience. You want to get that homogeneity of coverage. And then kind of talk about sort of flexible BIM coordination. And often this means that, at the sort of tail end of a project, when the sort of installation is happening, there's often times where things need to move, things need to change to actually be able to work as part of the sort of the design on site. And often you'll have to change speaker positions. And that can be really detrimental to the loudspeaker design, often, the loudspeaker system design, often. But we have a sort of a real flexibility with HOLOPLOT to be able to re-optimize and kind of align our beams to be able to work with that. And that's something else that we'll look at and cover in a second. So project budget is also something that sort of comes into play here. And we talk about this as kind of how sort of innovation meets cost. Because with the sort of the technology that we're talking about now, the ability to use these coverage beams to cover large open spaces to minimize the actual number of loudspeakers and mounting positions that you're using, you ultimately then reduce your installation efforts, which reduces cost. There's a reduction in required mounting furniture. So we talked about the kind of the totems, the pillars, the canopies that are often needed on sort of train station platforms. If you can reduce the amount that you're doing there, the amount of sort of cable trays that kind of it all comes into play. If you can make a reduction there, then you can ultimately drive down the overall project cost. Less requirement for acoustic absorption as well. Again, if you're able to control the actual dispersion pattern and keep the sound off of the surfaces and not excite the space in the same way, that you can reduce the amount of acoustic absorption required and still meet those intelligibility standards that you want to as part of your design. And then sort of general sort of reduced maintenance efforts if you're reducing the number of fixtures that you have. So all things to sort of take into consideration when sort of planning a project and sort of planning the budget for a project. And certainly when you're using a HOLOPLOT system, a number of those things will come into play. So why do we need coverage beams? And first of all, just a very sort of quick recap in terms of sort of the technology there. So we move from kind of a standard point source where you've got no real sort of control over the sound propagation, and then it's mechanically steered, and the fact that you have a fixed both vertical and horizontal dispersion pattern that you have to play with, and all it is about aiming the speaker to be able to get the coverage that you want. Then it kind of moved into sort of line array systems where you start now to have a certain amount of control then in the vertical, and you're able to sort of steer in the vertical and control the sound in that way. And then, you know, the next step in that evolution is the HOLOPLOT matrix array, where we're then able to steer in both the horizontal and the vertical. And then coverage beams go a step further in terms of the optimization algorithms that we use to be able to get that evenness of coverage and that spectral uniformity throughout the area that you're actually trying to cover. So let's have a quick look at that. So just to kind of then quick recap on that, just look at this slide. So it's the coverage beams that we're going to look at, and that's part of the 3D audio beamforming side of the technology. So looking again at these, so here's sort of a coverage beam. This is where we kind of designate an audience area. That can be any shape. It doesn't actually have to be a square. It can be a completely sort of tailored shape in terms of where you want to have your audience and where you want to achieve that level of coverage. And again, sort of within that space then, you've got the homogeneity of coverage and spectral uniformity using our optimization algorithms. Ultimately, that reduces reflections because you're able to control the sound all within that space itself. You get the improved intelligibility on that space because of the reduction in reflections that you have there. And then every audience member gets the same experience, which is ultimately what you're always trying to achieve as a designer. So looking at kind of the SPL mapping in that, and you can see very clearly in terms of the level within the box itself, and then how that steeply rolls off outside of that box. And we can't just do it for one area. We're actually able to do multiple zones. And from a single array, you can do 4 of these coverage beams. In this particular instance, you see that there is 2 coverage beams running simultaneously, each with its own content, EQ, level, shape, and directivity. So you can ultimately have different content in those boxes, or you can have a number of these coverage zones from the single array, so up to 4 from the single array, and achieving the same thing in terms of the homogeneity of coverage within that, but also that separate content. So how do we work with coverage beams? And this kind of going into a little bit into kind of our workflow and how we use our software to be able to create these coverage beams. So let's have a quick look at that. So there's kind of 3 steps to this, I suppose. We start off with the actual drawing of the zones. We move through to set the optimization parameters, and then we simulate and actually deploy them. So let's have a quick look first at sort of the drawing the zones. We start off with the 3D software. Often our models come in using you know, a CAD or a Revit or any of those kind of architectural 3D modeling software platforms. We often take those models and take them into SketchUp and simplify them down so they work acoustically. Then within SketchUp, we're actually able to sort of say bring in that existing venue model, create the zones and the objects within SketchUp, and then export them from that into HOLOPLOT plan, where they come through with the zones obviously already designated, and the full kind of architectural model in there. So then we set the parameters within HOLOPLOT plan, and let me show you what those parameters are that we're actually able to control in there. So the array configuration, we can do that 2 ways. We can actually initially set that up in SketchUp and import that through, or we can actually design and put those in within plan. And we can adjust that configuration within plan as well. The beam and zone definitions in terms of what you're trying to achieve with those zones So you can set the zones up either as an audience area, so something you want to try and cover, or that zone can be an avoid area, something you're actually purposely trying to keep sound away from, which is often happens in our designs in terms of wanting to keep sound off sort of reflective surfaces, for instance, or particular areas of, let's say, an auditorium that you're trying to cover. And then we've got the ignore sort of zone as well, where the actual software doesn't think about it, and it just sort of acts as sort of a boundary within that space. We also then can adjust the target SPL that we want to be able to achieve in that space, the frequency response in the way of a target curve, so we can actually adjust how we want the system to respond in terms of frequency across the entire audience area that we're trying to cover. We can adjust the phase response within that as well, and the level drop over distance. We'll take a look at that in just a little more detail in a second. And once we've done that, yeah, we are then able to actually simulate that and pull out SPL mapping from HOLOPLOT plan once we've set all those parameters within the software. And then obviously from that point, we then are able to deploy that onto the system itself. So taking those plan parameters and looking at the deployment. So we take the plan parameters, they get sent through to the controller, which is a 1U rack that sits, and all that does is actually then send the configuration in terms of the actual beam configurations through to the actual module itself, which has an inbuilt FPGA, which then sort of takes that information, and that information consists of, you know, the gain, delay, and the filter settings within that. And then obviously then sends that through on an individual driver basis through to the module itself to actually produce the beam within the module. So then just to kind of recap on the sort of the coverage beams and the optimization parameters. So we can adjust things. So target level is one thing we can adjust. Which areas need to be covered, which zones must be avoided. Level drop over distance. So which level distribution over distance is desired? You know, if you actually want it to behave like a line source, for instance, and you want it to drop off over 3 dB of doubling of distance because you want to use all of the energy at the front and actually don't mind that it drops off over distance, then you can use it in that way. Target frequency response. So which tonal balance is preferred? Do you actually want sort of a haystack in the low end because you're mixing something maybe more music with maybe sort of a rock show or something like that, where you really want that drive in the bottom end, then you're able to kind of set that target response appropriately. The target phase response, and this is a trade-off between phase linearity and latency of the system. So aligning the kind of phase of the system to the point where you get linear phase beams, which are kind of the highest sort of optimized beams in terms of linearity, but you could also have the minimum phase beams where we reduce that phase linearity, but it really does reduce then down the latency of the system to very, very low levels indeed. So it depends on how you want to work with the system, whether you want to work with it in a live environment or whether you're actually starting to use sort of using canned content in terms of how we use that. And then air absorption compensation, sort of how much air absorption compensation do you actually allow at long distances? If you're throwing sound over very long distances and you need to compensate for that air absorption, then you can adjust that as well to ensure that you kind of maintain that level of distance. And so I think on that note, that is kind of a very sort of brief kind of overview in terms of coverage beams. Now, what we want to do is do a bit more of a deeper dive, and we actually want to get into a case study. And at this point, I'm going to hand over to my colleague Emad here, who's going to take you through exactly why a coverage beam is successful and a real-world kind of deployment that we recently did, which highlights that. Over to you, Emad.
Thank you, Gareth. So let me say, I will go through this case as a real word that fits very well in what Gareth introduced now. It's a very brief introduction to this case, but I think I will try to focus on what is important in this. The case is our recent installation in Masjid Misr. Masjid Misr is, or translated from Arabic, excuse me, is the Mosque of Egypt. And that is a recent construction in the new administrative capital of Egypt. It's the central venue of a bigger complex, which is the Misr Cultural Islamic Center, that includes other buildings, other venues, other facilities, which are all concerned with the religion of Islam, its teachings, and its culture. It's called also the Grand Mosque of Egypt. That's the official name, and it's actually grand in the sense of the word. It has a floor area of 10,000 square meter indoors that can accommodate up to 12,000 congregation members. It possesses a very unique architecture. Its interior design is actually a piece of beauty from inside. But that comes always with acoustic price, as you may know. And here, for example, we have a dome in the center of the room, and that dome has a 60-meter high apex. We have also very challenging interior finishes from the acoustical perspective. Large, extensive walls, side walls, front, back walls are all covered mainly with marble or other materials which are equally hard acoustically. There are also 12 huge pillars inside the mosque, which are all marble or also hard surface covered. The ceiling is not necessarily absorptive, although it has some absorption capacity. And the floor, which is probably the main absorption surface in the room, is covered with carpet, but that is of course effective within a certain range. All these parameters together lead, of course, to expectedly long reverberation time. We were there on site to support the team of audio technology, our integration partner in this installation, and our task was supporting them in the testing and commissioning of the system. We did not have the chance to run room acoustic measurements. And as you may know, measuring reverberation time according to standards in this huge room using omnidirectional sources would be a challenge, would be not easy. And what we did actually is that we, of course, performed measurements for our system using our arrays, not omnidirectional sources. And with these measurements, we found that we have reverberation time values of 5.2 seconds in the lower mid frequency range. But as Gareth explained, our arrays are actually intended to avoid the excitation of the room, to minimize the excitation of the room. And of course, there is a huge difference between exciting the room with omnidirectional sources and with our arrays. That's why it's expected that the reverberation time, if measured properly, will be longer than this 5.2 seconds in this frequency range. We use the values, however, and our simulation models to estimate the reverberation time in this room, and that's about 6 seconds in the same range. The system in this room had a number of requirements. Of course, the main purpose of this room as a mosque, as a worship house, is listening. So people will go there to practice prayers, to listen to sermons, preaching, and that means that the speech will play the major role in all the activities of this room. However, it was required that the speech intelligibility in this specific room would be higher than usual. That was one of the demands. That means we don't speak here about lower SDI values or alarm system rates. We speak about quite higher values than that. And together with this, it was also a requirement that this will happen without changing the nature, the architectural nature of the room. That means, yeah, what you might think is that, okay, we have challenging acoustics and we want to have higher speech intelligibility than usual, then let's apply some sort of acoustic measures. And that was not desirable at all by the interior designers and by the architects who wanted to have that at the minimum. Mainly the side walls, the back walls, the front walls should be kept intact. And if there is something to be applied, that should be in the very, very minimum. Together with that, they wanted also to hide any loudspeaker system. So we want to have the system installed, achieve that higher than usual STI values, speech intelligibility, without applying treatment extensively and without also having the system visible. For the same purpose, they wanted to keep that seamless tone of the interior of the room. In addition to that, we had the usual requirements, of course, even coverage of sound pressure level. We wanted to have minimum echoes, which are not unusual in a room like this, especially with these surfaces, hard surfaces, and with this dome. We were also experiencing the lot of coordination that happened during the coordination phase with the architects and the interior designers, who wanted always to be doing this flexibly, which is understandable. There is always something to move, some items to introduce, lamps, ornaments, arts, pieces of art, and other things. And there were possibly conflicts, and that's why we had to be very flexible in coordinating these locations, the locations of the speaker system. Together with the system consultant also, we were actually doing this very well over the course of coordination. And just to summarize all the requirements, that was required, of course, to happen without excessive costs. Here is a model of the mosque, and we can see here the primary dimensions, 100 meter by 100 meter, which will make together the 10,000 square meter, also the dome with its 60 meter high apex. But also we can see the arrays, the HOLOPLOT 9 arrays that were used to meet all the requirements that I've just gone through. Maybe one thing I would like to mention here is that originally we had 6 locations, not 9 locations. And with the 6 locations, we were still able to meet also the targets, all the targets. We went to 9 because over the coordination phase, we had to divide some of the arrays into 2. And that resulted in a higher number of positions, but it's purely for coordination purpose, not for performance purposes. Here I'm showing what we have again in the model from a different perspective, and I would like just to briefly describe the concept that we developed here to achieve the coverage of the room from 9 positions. It's based on dividing the entire area, the entire prayer hall, into a number of sub-areas, and these sub-areas are then covered by dedicated arrays. So we wanted to cover always each sub-area from one array, and we wanted also to make sure that that one array is covering only that sub-area. This is possible because we have the horizontal control, the tailoring of the beams to fit over specific target areas, and also to avoid other other areas and room boundaries. And we have, after all, these optimization algorithms that stand behind the hardware. The advantage of doing so is that we can make sure that any position in the room, any congregation member would be covered by one array effectively, not by two or more. And that is very desirable in a room like this, in a system like this, because here we don't speak about spatial sound or immersive sound. And we actually want to achieve this through coverage from one source only. Increased number of sources in the room would or could lead to a lot of issues, like, for example, decreased direct to reverberant ratio, because one speaker will send the useful energy, but the other speakers, which inevitably also sending energy, will not be considered useful but harmful, and that will contribute to the reverberant part, not the direct part. Decreased speech intelligibility, increased possibility or probability of echoes in this case, and of course increased interference. So through this approach, we wanted to make sure that each position in the room will be covered by one array only. And this array is avoiding also sending energy in the other areas. That was the main purpose. We can speak here about that concept of tentatively called now virtual barriers. It's like looking at the subarrays as compartments, and each one of these compartments will be bound by a number of virtual boundaries to make sure that the energy from one array or from one area is not spilling to the neighboring area. That's just the way we wanted to achieve best control of the sound over the audience areas. As you can see here, we have also divided or used these names over all the course of the project. We have the frontal area, we have the central area under the dome, and we have back area, and then we have two sides or wings. And these are the names that were also given to the arrays covering them. Let me take you briefly through the individual parts or the individual sub areas in the room. The frontal part is covered by 4 arrays, all concealed in the front wall invisibly. And these arrays are of 2 types, 3x1 and 2x1, so they are not too large. They are devised to or instructed to mainly avoid also the member and the mihrab positions where we have microphones, open microphones. And that is something that we can do also relying on our technology and our optimization algorithms. And in doing so, of course, we can improve the gain before feedback significantly, because we make sure that the energy spillage to the microphones in this case would be significantly minimized. But even here, the spillage of the energy that goes deeper under the dome from these frontal arrays is not necessarily harmful because it's aligned with the rest of the arrays. They play even a useful role, a positive role in localization. We are using this spilled energy to draw the localization, to draw the image towards the front wall where the imam is standing or kneeling. That made sure that everybody actually in the room would have the localization towards the front wall, not hearing from overhead or from the sides. To the right of this slide, you can see the simulation results of this frontal part only with these 4 arrays, and you can see that we are showing here the direct sound pressure level distribution. We achieve with this array this uniformity, 89% plus minus 3 dB, within plus minus 3 dB over the targeted area. The rest of the audience areas are avoided, are undesirable, and we achieve separation of 13 decibel in the 1 kilohertz octave in the speech range. I just want to make sure that you understand this is the direct sound pressure level, not the total sound pressure level, which means that we are not relying on the diffuse field, for example, to achieve homogeneity in this case. Here are the two sides. The two sides are the bigger arrays. They are 4 by 2 each, and we do the same. We are also using the 2 arrays to cover the side with a tailored beam that looks like the image here to the left. And as you can see, it's creating a kind of a sound corridor that can be actually very tight in the width, because it's 100 meters in the depth and 18 meters in the width. The array also is mounted at relatively high position. It's 7.5 meter center array from the floor. And that makes sure also that the angle of incidence will be not really in the grazing region that can causes absorption, extra absorption, or even shadowing if the array is brought down, like the case with other technologies. And again, to the right, you can see the simulation results. In this case, we have here really that kind of homogeneity over 100 meters deep in the room within 84%. That was, by the way, all confirmed and validated on site by means of objective, but also perceptual listening tests. And you can experience this there by walking from the back wall to the front wall and really feel how barely the loudness of the system will change. These are the dome arrays. The dome arrays are 2 arrays, each is 2 by 2, and they are sharing the area under the dome. But again, each half of this area is covered by 1 array with a kind of smooth blending of energy into the other half. Just to let you know, this is these arrays are mounted at 23 meters from the finished floor level, and they are separated 21 meters. So it's also that lateral spacing that is very unusual for any other technology, and that is possible in this case because of the horizontal control and the optimization. So in the dominance area of any one array, you have the energy coming from that array, and what comes from the other array, which is 21 meter laterally spaced, will be too insignificant in level. It will come, yes, late, but it will not be loud to cause echo issues. And in the area between the 2 arrays and the border of the 2 arrays, yes, the levels are comparable, but the arrival times are comparable too, and that's the reason we don't have echoes under this dome. And again, it's all because of the technology and the fact that we can control horizontally. To the right, you can see the sound pressure level distribution in this case, and we have a bit higher uniformity, a bit less separation from the rest of the room. That was on purpose, and that is something that we do as a trade-off, because as Gareth showed, we have a number of variables that we can play with, and these variables can be even set with a certain level of priorities depending on the project. The last thing is that back array, and the back array is covering a large area of 25 by 50 meter. It's a 2 by 2 array mounted in the ceiling, hidden completely in the ceiling, and it covers that area with this uniformity that you can see to the right. Again, we speak here about the direct sound pressure level only. Now let me show you the sound pressure level distribution of the entire system. Now we are not looking at individual arrays, but all arrays are active, and here is the total sound pressure level with these values. I would just mention 2 things. First, we are showing to the left the standing ear height, and to the right the kneeling ear height, 1.75 or 1.7 to 0.75. about 1 meter difference. And we achieve here more or less the same performance at the standing and the kneeling ear heights. And here we used 1 beam, not 2. We're using 1 single beam, which is optimized to cover the 2 ear heights simultaneously, which means that we don't have 2 beams to switch between, or we don't have to compromise between the 2 heights with another height, a third height in between them. These are done with 1 beam only. The other thing I want to mention is that this 84 dB is just an operating level, but we have a lot of reserves in the level. This is enough for the audibility, for the speech intelligibility, without also triggering the signal masking effects in this case. This is the target direct sound pressure level. The last one was the total sound pressure level. Now we look at the target sound, direct sound pressure level, I'm sorry. And the direct sound pressure level is achieving even more impressive homogeneity, uniformity, if we keep in mind that this is not getting any support from the room. It's uniform within 90% plus minus 3 dB. And that is something also that you can see and notice in the plots here. And again, kneeling and standing are more or less identical. This is probably the most important metric that we look at, the speech transmission index in the room. And here again, we compare the standing and the kneeling. The standing and the kneeling are showing more or less the same values. And these values in the simulation, we had over 90% of the points within this range of 0.54 to 0.72. Measurements on site were showing, of course, with far less measurement positions compared to the calculation positions in the simulation, but we had comparable results, close results of 0.53 to 0.69. Average was close to 0.6. But these are all under no occupancy at all. So we don't have here in the simulation and in the measurements, we don't have audience in the room. When, of course, we have audience, that will have other implications. Okay, I see the time is running. I will try to run through the rest. What I wanted to say here is that now we even don't speak about band F as a target, but we can move to band E with these results of speech intelligibility. That means we go from just good quality system to high quality system, as called also in the standard. Here is direct to reverberant ratio. Without going into the math or the details, it's a ratio between 2 energies, and as you can see, energy that come early to energy that come afterwards, and you can define the border between the 2 energies by means of this TD in this equation. This TD might be, you have heard of C50 and C80. When TD is 50, it's C50, and when TD is 80, then it's C80. And these are all used to describe properties of the room in the first place. So they are intended originally to be measured with omnidirectional sources and omnidirectional microphones to describe the room rather than the system. We can also use it with systems. And here we can use the TD to be the flight time only of direct sound. That means we really strictly look at the energy of the direct field to everything else that comes afterwards. And this is function normally of the reverberation time of the room, of the distance between the source and the receiver, and of the source directivity. I'm showing here some simulation results of the direct to reverberant ratio in the room. By means of this simulation, you can see that we are achieving in the 2 kHz octave, as an example, positive D to R values. And here again, I speak about D to R in the strict sense. That means direct only to reverberant only. Keeping in mind that we have these distances. So we achieve direct to reverberant ratio, positive value on average, from these distances, even look at the sides, we are able to achieve positive D to R ratios at the rear of the room and under these reverberation. As we mentioned echo already, I'm just showing the echo criterion, the speech, which also shows here that we are achieving EK speech under 1, almost over 90% of the calculation positions. That was again validated on site perceptually, where we don't actually feel echoes, any significant echoes or noticeable echoes in the room. In the coordination, as I mentioned, we had to be very flexible, and that was possible because we were able to do more than usual, normal, classical approaches. Our arrays are hidden behind screens. The impact of these screens were also looked at, and it was tested sometimes here in our headquarters, and we found that there is no issues. Our possibility, or the possibility that we can take the arrays that high to 23 meters, for example, under the dome, where was something that was very much appreciated by the interior designer, because in this case we were very far away from the site, and also we could go away from any conflicts with the other items in the room. In some cases, even we can compensate for screens that cover our arrays, because after all, we have this optimization tool, and the optimization can look at what is negative caused by the screens or the meshes, and tries to compensate for that. But in this case, we even did not have to do this. This is another image showing the positions of some of the arrays. Some of the arrays were hidden here next to the mihrab behind the copper screen. And these two arrays under the dome are, they could have been also completely hidden and made flush with the wall, but the height is extreme. And of course, we cannot steer energy 90 degrees. That's not yet, maybe, but it's not, it doesn't make sense to do this. That's why we had to make some sort of mechanical inclination, and that was the result. Well, I am closing with this, let's say, summary. We have certain features, we have certain capabilities, like the control over the horizontal radiation, the possibility of optimization and selecting targeted areas, voided areas, and the general term of beam tailoring and creating really 3 audio beamforming. Here in this case, that was used to have maximum inter-array spacing. We had really large spacing, unusual spacing between the arrays. We could do this here. We have also minimized the spillage onto side walls and the dome and the boundaries in general. We were very flexible in the coordination phase with the interior designer. We were able to move, we were able to divide the arrays, and we were able to go higher unusually, and we achieved higher gain before feedback. And finally, we also, as I said already, we were able to mount our arrays very high, which is not typical for classical approaches.